we're going to look at nuclear transformations. So the definition would be the conversion of one element into another element. So for example, 100 years ago, Lord Rutherford did this nuclear transformation. It was nitrogen 14 plus an alpha particle became oxygen 17 plus hydrogen. Another example of a nuclear transformation was Irene Curie. She was Madame Curie's daughter and her husband. They took aluminum 27 plus an alpha particle, and they made phosphorus 30 plus a neutron. So these are just two examples. Okay, particle accelerators. Alpha particles and protons are accelerated in an electric field. And it's the conversion of kinetic energy into particles. Experiments with particle accelerators have led scientists to postulate the existence of the strong force, the weak force, and the electromagnetic force as important in the nucleus. Particle accelerators give particles very high velocities, and positive ions are used to bombard the target nucleus. So here, for example, we have hydrogen plus a neutron. We get two hydrogens plus this is an antiproton plus a neutron. Let's look at the energy of nuclear reactions, specifically the mass energy equivalence. So we have the formula E equals mc squared from Einstein. C is the speed of light, 3.00 times 10 to the 8 meters per second. So to any mass, there is an associated energy, or to any energy, there is an associated mass. So we can take this equation and we can call it delta E equals delta M C squared. Our first problem gives us 393.5 kilojoules is released when 1 mole of graphite is burned in oxygen. It's asked for the change in the mass. So energy is given in units of kilojoules. So the first step is to change the kilojoule units. We need to remember that 1 joule is the same as a kilogram meter squared per second squared. So if we have a negative 393.5 kilojoules, remember it's negative because it says that the kilojoules is released. Energy released would be a negative value. We take the kilojoules and convert them into joules. So the kilojoules units cancel. And then we just said that 1 joule is a kilogram meter squared per second squared. So the units of joules also cancels. So then we substitute this into the equation of delta E equals delta mc squared. And we get our change in mass. So here's solving for delta M. And then we get this very small number, minus 4.37, 10 to the minus 12 kilograms. So we can do another type of problem, and this problem is giving us a nuclear equation. The nuclear equation is uranium-238 is an alpha emitter. The question is asking for what is the change in mass. So we're given the AMUs. So uranium, the AMU is 238.003. The thorium-234, the EMU is 233.9942. Helium is 4.00150. So these are the AMUs. So we're going to want to take the sum of the products and subtract the reactant. So this is the sum of the products. It's an AMU. We subtract the AMU of the reactant, and we get 0.0073 AMU. So now we can do thermodynamic stability. It's the energy released per nucleon. We're going to use delta E equals delta MC squared. So here's our problem. We're given the mass of the nucleus. We're given the mass of a hydrogen atom. We're given the mass of an oxygen-16 nucleus. So first we want to know what is the change in mass for the formation of 1 mole of oxygen-16. So to form the oxygen-16, we need both neutrons and protons. So we have to, given the oxygen-16, we have to write this equation. We're always going to use neutrons. We're always going to use hydrogens. So we needed 8 neutrons. We needed 8 hydrogens in order to get this oxygen. We're going to use the sum of the products minus the sum of the reactants. So here's our product. That's the mass of the product. Subtract. Now we have 8 neutrons, so we're going to use this 8, and we're going to use this 8. We have 8 neutrons and 8 hydrogens. So this 8 is used here, multiplied by our mass. This 8 is used here, multiplied by our mass. And we do that, and we get a negative 2.26 times 10 to the minus 25 grams. So if we're trying to get our units into grams per mole, we will have to take our grams per nuclei, or nucleus, and multiply by Avogadro's number, and then that will give us our units of grams per mole, and it's a negative value. Okay, that's enough for this time.